after he did the master doing his army service, and he wanted to do research in Tel Aviv because he continued to do the service here in Tel Aviv. He got a 1 year plus vacation, paid vacation from the army. He chose to do research in my laboratory. He actually started a new field of research in my lab, something that is around, but not many people in Israel and in the world know how to really deal with the mathematics and the physics involved, and they will tell you about it. Ron is graduating soon, hopefully. He submitted his thesis, and he's quitting the army and start a job in Classic, the quantum computation software company.
Thank you very much for the introduction. If anyone of you has a clicker or this also, I think.
I think
it's okay.
It's okay.
Thank you very much. So, and thank you for coming. We're going to talk today about, generally we're going to talk today about quantum computers, but more specifically, we will talk about quantum error correction. So the topic of the lecture is about a technique in error correction. It's called surface code under error model, which is new, where we see coherent errors on the surface code when it's Qubit-dependent errors, and I promise it will be explained till the end of the lecture.
Do you switch it on? Do you switch it on?
So, to those of you who missed the quantum computing revolution, just a quick review. So the world is trying to develop quantum computers. Those computers will solve important and hard problems like cryptography encryption to find the enemy's secret and to simulate large molecules, drugs, medicines. Those applications are practically impossible for a classical computer. Take like age of Earth to simulate. So we need a quantum computer, let's agree with that. But we want to talk about implementations and not about application. So what do we need to solve this problem? We need a computer which contains like thousands of qubits without noise qubits, and we can run algorithms. Qubits mean quantum bits, just like classical bits. And actually, because there is noise and the world is physical, so each one of these logical qubits is replaced by thousands of physical qubits. And if you make the multiplication, you have millions of qubits. So as you can guess, it's very hard to implement such a thing. So when you saw that IBM a month ago published that they have a quantum computer with 400 qubits, they have 400 physical qubits, which mean less than a half of one logical qubit. So it's important to notice, and we will understand the architecture behind all those physical qubits. We can implement, as IBM is implementing these computers with superconductors or atoms, acid rejective, and one of the leading architecture is photons, mainly led by Psi Quantum, a company which is very strong in this field, and by the quantum optics experts in our lab, led by Chaim and Chaim Moshe, Jonathan, credits in the end. Okay, so this is one of the architecture. We can each qubit can be replaced with light, with photon, and we can encode the quantum information in the light at the position of the photon. So we have a silicon photonic chip, basically. There are waveguides on this chip, and we can put the photon at the top rail or at the bottom rail. A top one will mean it's 0, a bottom will mean 1, but we want it quantum, so we want to make superpositions. So once we couple these two rails together, the photon will start to change population. It will be in a superposition which depends on the geometry of the coupler. So in the middle here it will be a 50-50 population, and we can make an X gate to flip the population from 1 to 0 or 0 to 1, and look at also the velocity that tells us we can start at the 0, and we go through 0 plus 1 till we finish exactly at 1. So far no errors in this architecture, but since the geometry is not accurate, so we plan one geometry, but there are complications there, so we get another geometry. So instead of a 1, we get 0 or 1, depending what we start, we get the 0 plus superposition of quantum superposition of 1 with some small amplitude. So it's a lot of zeros plus a little bit of 1. Why? Because of fabrication errors. It's not exactly when we planned it to be. So this is where my instructors at the start of my thesis came with the invention of the composite pulses. The composite coupler technique tried to solve this problem. What they did, they took the coupler, divided it into segments. Each segment has different geometry, and with different geometries we get different coupling, different tuning parameters, and we divide the path so we can get gradually something which is more accurate with a smaller coherent error. So this was the invention. Credit's not for me, because my mission was, they asked me how it affects the big picture. So I improved just one qubit, one gate, how it improved the big picture. And if you remember again, the big picture is quantum error correction. Because as we say, the big picture is that we replace every qubit with thousands of physical qubits, and we want to understand together the concepts of error correction. So let's start with the classical case to understand what is error correction anyway. Alice wants to transfer a Bob a message. She wants to transfer 0101. There is a noise. So it's not exactly 0101 because the decoder of Bob, in some probability, we see a 1 or a 0, which is a flip in some physical noise probability. So how classical error correction is solved this? We have an encoder which replaces each of the bits in a packet of bits. So the zeros are replaced with the packets of zeros. This way, after a noise, the decoder can look at each packet and decide what was the original information by the majority. So majority of zeros is probably a 0, but there is in some case still that there are 2 flips, not probable, with smaller probabilities that were 2 flips. But we still get a smaller error probability. So this is the basic idea of error correction. Questions so far? The same is with quantum. We replace every qubit with many qubits, like a packet of qubits, if you like. And this is in the physical world, but if we talk like about computer science, quantum computing is also a field under computer science, not just under physics. And schematically, we talk about the most common code is surface code, which is most commonly implemented in, for example, the IBM computers and atoms. Also a very similar code with the photonic architecture. So schematically, we have a data qubit, a physical qubit. We mark it with a white dot, and we replace it with a 2-dimensional array of data qubits. So all of this is just one logical qubit with many physical qubits. And using measurements that are called stabilizer, we can track and detect errors and to correct them. So those stabilizers finding errors, and the ancilla qubits in the middle, there are those that we make the measurements on them. So to find errors, and we'll see how it is working. So this is the basic idea. Let's assume to start that there are no errors at all. So if before we say that a 0 is replaced, a logical 0 is replaced with 0, 0, 0. So this time, in this specific surface code, logical 0 will be a quantum superposition, not just one state, but the quantum superposition of, might be complicated, but once you understand it, of all the possible cases, like you can think about it as parallel worlds at the same time, because it's quantum, of the cases where there is even amount of strings from left to right. So you see here that the pink dots are ones, all the other whites are just zeros. So here I have 0 strings from left to right. Here I have 2 strings from left to right. Here I have 0 strings from left to right, plus all the possible combinations. And this is a logical zero. Okay? So if I want to flip and ask myself what is the state of the logical one, it's a superposition of all the old states, and if I want to switch to this one, I have to operate with a logical X gate, which is a chain of X's. So I add one more chain from left to right. So this one becomes this one becomes 3 strings, this one becomes 1 string from left to right, and this is the logical one. So this is the basic idea without any errors. Questions or so far?
What are the X and Y axes of this?
You can think it about space, dimension.
Space.
Just a physics. You can look at the cheap IBM computer. They are just like on a chip. They are in a 2-dimensional. In photons, I have slides I can show you after
Each
that.
circle
Each circle is a qubit. Qubit, which is over there and
is
located.
connected in 4 wires to
Yeah, just to its neighbors.
neighbors.
In the case of superconductors, in
And
the
what's the
case of
difference between X and Z connection?
those are different. This is XXX measurements, and those are ZZZ measurements to detect different types of errors. At photons, it implemented a little bit different, but for the schematic understanding, this is enough.
Thank you.
And let's understand now how we can detect errors using this technique. Let's look at the surface. We start with the surface with no errors at all. Let's say logical 0, for example. The decoder, actually a classical computer, is making measurements all over the surface. It measures the black qubits, and it tracks the result of the measurement. As long as the measurement did not change, everything is okay. But if an X error will occur to one of the qubits, let's assume again just one error, the decoder will see a flip at the measurement. It was plus changed to minus, and vice versa. And there will be a classical algorithm that will say, okay, between those 2 flips, there was probably an X error, so I can track it, I can correct it, and I can track one error case. So you probably think that one error is okay, but I want to deal with multiple errors. What happens when there are multiple errors? When there is a X error, one qubit and another qubit, there will be 2 flips here, so the decoder will not see it. But at the chain, we will see the flip at the 2 edges of the chain. So it might sound perfect. We can track all errors, we can correct all errors, but now I want to show you what a logical error is. And a logical error means that the decoder could not handle yet, even by the encoding, it cannot handle the errors. So when a logical error happens, let's look at the following situation. I showed you that, and this this type of error, I see the decoder C minus here and here, but the same result will be when there is an X here and here. So the decoder has to be smart enough and to think that the actual error was the one that's more probable. So which one is more probable, the right picture or the left picture? The right picture, because it's more probable when there is something that happens in small probability, that will be less of it. So what it should do, it should guess that this is the error, but still there is a chance that this one, right? Even if it guessed this one. So in this guess, he thought these are the errors, he corrected them. Actually, the error were this. So we actually created a chain of x's. And if you remember the slide before, the chain of x's from left to right, they flip a logical 0 to logical 1, which is called a logical error. And now to return to the first slide of applications. Now we have this architecture to implement a quantum error correction, which is good enough for breaking encryptions and simulate molecules. So we need 10 to the minus 12, 10 to the minus 17 error rate, which is very, very small. So we can guess from combinatorics that I just can increase the surface size. And this way to suppress the logical error, smaller logical error this way. And simulations from 10 years ago tells us that we can increase the surface. They tell us take some surface size, take a physical error rate, and I can tell you from the simulation what the logical error rate is. So everything is okay, right? But this error model is not the same error model that I started to tell you about, with the couplers and the photons. This is not that X and Y and Z happen in an accident in some probability. X happen all the time. Every time the qubits go through the coupler, there is an X happening in a superposition of plus just a little bit happening. So this is called coherent errors. And we want to treat this kind of errors. And before going to literature and see what they did with that, we want to understand how coherent errors behave on the surface. So once again, we start with a logical 0, which is no errors at all. And we want to start and explore what happens when we apply coherent error. So we apply coherent error just on the first qubit. And all the other qubits, no errors at all. So there is a superposition of error didn't happen, identity operator, plus an epsilon with X happened on the first one. There's also other types of error, but we can still focus just on the X error. So the world, which is composed anyway of parallel worlds for the even strings, is splitting into 4 worlds. Error did happen plus small worlds or less probable worlds that error happened on the first one. But this is just on the first qubit, so now we have to apply on the second one. Question? Questions so far? So now we ask ourselves what happens when we apply it on the second qubit. So the world, from the same reason, splits again into 16 worlds. So you can guess how nasty it becomes when I continue to add more and more coherent errors. Those are coherent errors, and they are complicated to solve. And Chaim and Jonathan, they wanted an answer. Don't mess our head. We want to know what's the performance of our physical noise. So I went to the literature and checked what happens when there are coherent errors. And the literature is actually really new, just from 5 years ago. And actually all of them took the same coherent error for all the qubits. And this was not the case in our situation, because, as we say, the physical model was fabrication errors, which have some distribution. Some of them have one error, and some have other errors. So we need a tool to check what happened when the coherent error was not the same epsilon for all the qubits. Which means the Qubit-Dependent coherent error, which is the recent question. The way to use it, let's start to think naively, how can we solve this situation? We can say, okay, let's calculate all this epsilon, let's multiply epsilon square, epsilon to the power of 3, let's calculate all this epsilon, then make quantum simulation, where we hold on the information and we make like Monte Carlo simulations, and we know what the logical error is. But actually, when you try to think how much memory do you need in your computer to solve this mission, just for a surface at the size of like 12 over 12, you get megabits as the number of stars in the universe squared. It's really difficult to solve it the naive way. The approach was in a collaboration with Andrew Darmawan, who published an article about coherent errors 5 years ago, but he took the same coherent errors for all the surface, but this was the only tool that we can use, and just to change the coherent errors, they don't have to be the same. The basic idea, he converted the surface code into tensor network. The tensor networks is a mathematical representation of multiplication of many tensors together that represent the surface code. We can add a layer which represents the coherent error, or different coherent error for each one from our error model, make stabilizer measurements, and to trace everything, which is making everything equivalent to a scalar, and to repeat for averaging. The reason it saves memory is that instead of saving the quantum information for the whole surface, you make each column at one time. You look at the one, and then at the another, and you add it again and again, so you don't have to store such a big amount of information. Instead of exponential at the number of qubits, it's exponential only at the width. So before continuing to another interesting idea from understanding of different coherent errors, we can take the simulation, we run it, we can look at the results, and the composite pulses technique relatively to the uniform one gave a really amazing results of almost order of magnitude less qubits, which brings us more closer to implement a quantum computer, which is really amazing and interesting. But we want to continue in research, and we ask ourselves, okay, we have a tool that we can understand how coherent errors behave on the surface when they are different, and we came up with an idea which I will explain just now. When coherent errors is almost the same but different at the sign, and I mean that the coherent error, those epsilons, they don't have to be positive, they are complex. They can have phase, they can have a sign, they can be negative. What happens if the first one is positive but the second one is negative? Perhaps there are a combination of errors that are equivalent and can cancel each other with pluses and minuses. And I want to explain you the intuition to why is it true, and this is almost the end of the presentation, with the following example. We can let's look just again at the logical zero with just 2 strings and 0 strings. And I want to show you the intuition to why this plus-minus technique can be another approach to reduce the logical errors. Let's say there is just 6 coherent errors at the top over there in this pattern. So it's happened at both terms because it's in a superposition. So of course I have the terms a to the power of 6 when there are no errors at all. But some of the combinations are combination with XXX. When I do XXX here, I have 0, 0, 0, 1, 1, 1. Another combination is XXX 1, 1, 1. But notice this time it was a minus, because here there are just 1 minus, and here is minus multiplied by minus. So I have a plus. This is positive. Now, and this is the most interesting part in my presentation, let's look at the state which all zeros. For the same error, I have here a 1, 1, 1 here, because there's some flips, and also here. And did you notice any cancellation? You see those two are similar? Mm-hmm. So we can even suppress more errors, and we can simulate it using our tool. And we see also a very good improvements, 4 times less qubits per one surface, which is also a very interesting technique. This technique, this is just theory, but it will be very interesting to implement it maybe on photons. We tried it a little bit on small clusters with positive and negative error, the different couplers, like the length, the geometry can once be bigger, once be smaller. Also in ions or atoms, the electromagnetic field, which we know that in ions they suffer mainly from the phasing error, which can be a negative and positive coherent error, and also in superconductors that have crosstalks. So it's worth thinking about it. And that's it. If you find quantum error correction interesting, a small promotion. I am writing a newsletter, so you can scan the QR code and follow. And mainly to thanks and appreciate my collaborators from the Femto Nano Lab. Thank you for all the work together. It was amazing, and good. I'm open to questions.
Perfect.
In one of the slides you mentioned Shor's algorithm.
Yeah.